Yep.
Joseph's covering the applications of low temperature plasmas to human spaceflight.
Great. Awesome. Thank you, Wayne. So I am just finishing up my PhD at the ANU. So I'm with the Space Plasma Power and Propulsion Lab. So most of my work is on one, looking at plasmas as radiation sources and also looking at plasmas as tools for a bunch of different applications, many of which are space focused or at least space inspired. So start off with just, what is a plasma? So in a nutshell, a plasma is an ionized gas. That's a very broad definition because, you can have the solar, you can have the sun, you can have fusion plasmas, very, very hot, very, very dense, all the way down to the interstellar gas and solar wind, these very diffuse, sparse plasmas. So where I sort of operate is in these low temperature plasmas. They're somewhere in the middle. They're called low temperature because whilst the electrons have lots and lots of energy, the neutral gas atoms, the ions, they're quite cold. Okay. So why that is good is because you can have some sort of surface or a sample, and you can do interesting chemistry with that sample without basically destroying it with a massive heat load. And these sorts of plasmas, they're very common in gas discharge lamps, fluorescent lamps, also the sorts of plasmas you find in the semiconductor industry. So there's a few important parts of those plasmas. The electrons, they're doing a lot of the heavy work. They have all the energy, they're breaking bonds, they're exciting atoms. And you have ions, they're doing sputtering of surfaces and surface activation. You have excited neutrals and radicals, and you can do lots of interesting things like reduction, oxidation, nitridization, very useful. And then, of course, plasmas tend to produce light. A lot of it is invisible, but you also have the sort of deep ultraviolet, high energy radiation that can do interesting things like ionization, dissociation, and all of that you can get, different gas phase reactions, different surface interactions. So here are a couple of examples of plasmas that I work with in the lab, all radio frequency plasmas. And as the name sort of suggests, they're generated by exciting gases with radio waves. So here's a helium plasma, that's an oxygen and plasma, and this is something that you might see in semiconductor manufacturing, a hydrogen argon plasma. So these things have a few sort of novel properties and features that make them useful for lots of different applications. The first one, like I said, if you're in a low temperature sort of regime, you have very hot energetic electrons, but cold gas. You also have multiple energy channels. So depending on how you package your plasma up, you can either extract electrons or ions or neutrals or just light. So you can basically choose what you want for your application. You can also generate them more or less wherever you want. It's not that hard. You just need a power source, potentially a feed gas if the application calls for it, and then some sort of electrode. You can also do this in many versatile sort of operating conditions. So when you take a plasma and you kind of give it to a gas or a solid or a liquid, really two things happen. You either produce compounds, some of them can be useful, like ozone, nitrates, nitrites, hydrogen peroxide, atomic oxygen. You can also destroy, you can break things up. Some of them might be nice to break up, for example, PFAS, forever chemicals, volatile organic compounds, cellulose structures, all useful things to be able to break down. So in the context of these space missions, so a lot of the long-term planned stuff kind of operates as a camping trip, right? So you're bringing all your resources with you, you're reliant on resupply. That's just the way it is for the moment, but obviously that's not very sustainable for a super long-term independent colony or mission. So complete or near complete independence would really require being able to grow your own food, water and air, treating that, dealing with waste, all the different sorts of waste, and being able to manufacture things right there as you need it. So I'm just going to go through, I've cherry picked 3 different applications that I have some involvement in. Either I'm directly researching or I work with people who are researching, where plasma can kind of help in these areas. So the first one is plasma agriculture. Two words you wouldn't necessarily expect to put together, but there's a lot of interesting things you can do in the agriculture domain. A lot of interest here on Earth, kind of a new idea for the space. But the first one that I find interesting is inedible biomass recovery. So, you're growing a plant, you have some sort of crop that will have parts of it that we just can't digest, whether that's a root or a stem or a leaf. So here on Earth, you would compost that, you would get those nutrients back in the cycle that way, letting them decompose. That might not be quick enough on the moon, where you're trying to really optimize that and narrow those margins. So what you can do is you can expose that to an oxygen or a nitrogen plasma and break down those cellulose barriers and get things degrading quite a bit quicker, get them in the loop more rapidly. Another one is plasma activated water. So as that name suggests, you basically have a plasma and you introduce it to water. And if you have nitrogen or oxygen gases involved, you can generate these reactive oxygen nitrogen species in the water. Some examples of those are nitrates and nitrites. So those are very common ingredients in chemical fertilizers here on Earth. So in that direction, you can kind of take this liquid solution and use it as a nutrient source for your farming operations. You can also do pH control, which might be useful for sterilization or cleaning. And then, of course, you can also treat you can treat seeds and powders with either UV or plasma. That breaks down cell boundaries and in the lab has been demonstrated to enhance germination rates and growth. A lot of this work has been driven by the Applied Chemistry Lab, NASA Kennedy. I visited them last year, spent some time there. That was very good. Unfortunately, they're suffering a little bit with the NASA problems at the moment, but they did sort of a lot of the groundwork in applying this to space. Then there is in situ resource utilization, which needs no introduction. But when I say this, I'm really just talking about processing the lunar regolith. So I think it's something 40% oxygen by mass. There's a lot of oxides, basically is what I'm trying to say. That's no different to here on Earth, where we have iron ore, alumina, for example. To get to those metals, you need to take the oxygen off. You need to do reduction. So plasma reduction, that's not a new technology. That's been happening on Earth. Hydrogen arc furnaces are a thing. They're actually getting quite competitive now. But what we don't typically consider here on Earth is the oxygen that comes off, because we already have plenty of that going around. But on the moon or Mars, that could be quite valuable. So yeah, that comes out partially as water, partially as OH, both very useful. And there's also been some work done, not by me, but by others, on just plasma processing of the Mars atmosphere with the microwave plasma. And they're producing O2, look, fairly modest amounts that are fairly expensive, but I'm told this is actually similar to molten electrolysis of regolith. The MOXIE experiments are actually quite similar outputs just by doing a plasma process. Then there's dust mitigation. So, and I gave that a really good introduction before, and so did David with his book. So as we all know, this moon covered in this jagged, sharp, abrasive dust. It's a real pain. If you haven't read the Apollo transcripts, they're quite funny. Them dealing with this stuff, trying to vacuum it off, it doesn't work. Chemical methods are not very effective at removal. There's a bunch of other methods. Some electrostatic methods, so electron beam cleaning, the EDS system, very popular. We basically have electrodes embedded in the suit. Those are great. They do a good job of cleaning, but they don't work particularly well for the very fine stuff. And for our purposes, I'm calling that, less than 25 micron. So they don't clean it too well. If you use really deep ultraviolet radiation, however, the kind that we generate with plasmas in the lab, you can really blast that stuff off in a short amount of time without surface modification. And there's an asterisk there, which you can ask about later. But this is an example of us cleaning beta cloth. So it's a silica fiber that's coated with Teflon, I'm pretty sure. And that is allegedly a common spacesuit material. And this is basically just been loaded up with some JSC lunar simulant and just blasted off. Here are some microscope images. So what we did is we just took a sample, covered it in this dust, did a brushing vibration regime. You can see it's still pretty filthy. This is a lot of the 50 micron and smaller stuff. When you hit it with the plasma and the VUV, you really do make it quite nice and fresh again. Obviously, there's still a few bits and pieces hanging around. There maybe, in the 5 micron range or smaller, but it's much better compared to just electron beam cleaning, where you've obviously still got all this bits and pieces left over, the really fine stuff. Now, those were just 3 cherry-picked applications, but there is a lot you can do. So here is just a very simple sort of rough plasma-based architecture to support human habitation of these different environments. So this point, it's kind of still like looking at the art of the possible. So all of these processes, they've been well and truly proven in the lab. Many of them are actually in industrial use at the moment, but there's still the element of, does this make sense for the moon? So the inputs are fairly limited. There are still inputs that need to be brought in. And the challenge kind of becomes, can you keep all of this happening in a closed loop? And of course, there are many alternative processes. You don't necessarily need to do a plasma process to get all these resources. There's more classical methods where the advantage is here is that there is potential to do these all in a single sort of versatile system, which I think has a lot of potential economic benefits, a lot of potential engineering benefits than having individual specialized systems. So I'll leave it there. That's just been a very, very broad overview, but that's where I'll leave it.
Thank you, Joseph. That's excellent. I suppose that's one of the things to think about with the refinement of the technologies. I know you're working on the research stuff. It's getting the point where you've got it in a position where it can actually become industrialized to use on I suppose you could say lunar missions. It's getting all the things lined up so that can happen. It's something that we'll be working on probably in the next 10 years, which is the fascinating thing about it.
Yeah, there's a lot of, I mean, basically all of these things are applicable to Earth as well. So that's
Yeah.
where most of the interest has come through. Like a lot of these different applications, people have just kind of reached out to us and said, oh, hey, we're kind of interested in doing this stuff. Can you help us out with the plasma side? And then sort of more or less took the ball and ran with it to an extent.
Mm. Any questions?
I got a question, Wayne.
Yes, Alan.
Yeah, Joseph, is the production of plasma intrinsically energy intensive?
Not necessarily. So you can kind of get out what you put in. So
Yeah.
I work with plasmas that require, well, not require, but I can dump as much as 10 kilowatts into a plasma, but you can also generate one with a few milliwatts. It really just depends on how you're doing it. So a lot of these applications, it makes sense to kind of go big because that's where the scale sort of starts to favor you. But yeah, there's no reason, at least in the lab, where we can generate things with a whole wide variety. So industrially on Earth, there's plasmas that use tens of kilowatts to do processes. Direct treatment of gases, there's a bunch of systems in Korea that use 30 kilowatts, 30 kilowatt pulses. So that's very popular. Yeah.
Thank you. Thank
No
you.
worries.
Thanks, Lou. You're next.
Joseph, thank you for that. You said please follow up without surface modification.
Yeah. So that was about the dust mitigation with the really high energy ultraviolet. So there's a few materials that I would definitely not do this on, and that's part of what we've been doing. So that radiation source was originally developed as a simulation of the sun's really high energy UV to test material degradation. Some materials really don't handle that well. And it's kind of an interesting test because it's not something that you wouldn't necessarily see with the standard UV tests because they're much higher wavelengths, lower energy. So for something like that beta cloth, I haven't seen much in terms of degradation and something that you can see in surface effects, but quite a few polymer surfaces really don't handle well with that. So this is still something you could do, but you have to be very careful about how you apply it.
Also, I have another one. As regards, I noticed something about removing things like PFAS. There's a big problem around Williamtown, the airbase there, and
Yeah.
mountains. There are problems in their water supply. They've considered this process maybe to help in that way. Is that at that stage yet? It's too early days.
Yeah, no. So that's what I'm doing for basically all of this coming year. So we just got in a packet of funding from the Smart Sensing Network in New South Wales to look at deep ultraviolet based remediation of water contaminated with PFAS, and we're working with different agricultural groups to attack that. But yeah, again, exact same thought.
Excellent. Thanks for the questions. And also, Joseph, you'll be you've got a presentation at the IAC as well next month too.
Yep.
I think.
Yep, I've got
something else.
yeah, one presentation on the dust cleaning, and then
Dust
a
cleaning.
poster, I think, on interactive presentation, whatever that means, on the UV stuff.
Right, you've had two. I think Anna's got a couple as well, so that's great. Excellent. So thanks very much for your presentation.